Okay, good afternoon to everybody. And thanks for the chance to present this work, even in the not being present in such a nice conference. I will talk about some aspects of the KPZ equation, and the people indicate here corresponds to collaborators in one or another stage of the work. Just to give a few examples of what means a growth. There are some limited fusion aggregation or typical in which you have a Roth surface, or even in the simple model to the growth of a bacterial colony, the Eden model that shows also a Roth surface. And this is an experiment by Takeshi in Japan for liquid crystals, and this is for the growth of a surface. H is the imported field here. And let's start with equations. Till the 80s, what the most exploited equation was the Edward Wilkinson equation. That is essentially an equation with diffusion, random deposition, and maybe an external field that will not take into account the rest of the talk. In the middle 80s, Carter, Parisi, and Zhang extend, let's say, the Edward Wilkinson equation, taking into account the curvature of the front at the lowest level, and they introduce this term here that is non-linear. That makes this equation very particular. So let's start with the myth. The first one is that even some recent papers indicates that what is written here, that the KPZ equation is a genuine kinetic equation, because this deterministic drift cannot be derived from an effective free energy. But we have shown in this work that it is possible to obtain a functional from which we can derive functionally this equation, and introducing a kind of mobility, let's say. This model, this representation, resembles model A according to the classification of Hohenberg and Halperin. One detail is that if you make a discretization, you discretize this functional and projects in one of the directions, what you will find is this, you will find this kind of profile, and it is unbound from above, but has a bound from below. So as fulfills this condition, this F is the same F as here, is a Lyapunov functional for the pole. A second myth is that there are two main symmetries associated with the KPZ equation: Galilean invariance, reflection, dissipation relation. Focusing on the Galilean invariance, that is a property of the equation, of course, is traditionally linked to the exactness of this relation. Alpha, zeta, and beta are the typical critical exponents: the Roth exponent, the growth exponent, and the dynamic exponent. However, in this equation, in these papers, these we have shown that the form of the functional I have shown before make it necessary to do a consistent, to discretize in a consistent way both the Laplacian and the square of the gradients. Cannot be independent. But the discrete version obtained to this functional results that does not fulfill the discrete representation of the Galilean invariance. We have here results, simulation results, for several models, for the structure factor and for the width, and there is a shift in the curve because all of them follow in the same points, the same line, and we see that some of them fulfill Galilean invariance and some of them do not. In any case, all of them shows the same critical exponents, and the critical exponents define the universality class KPZ. Hence, this is, even though the equation fulfills Galilean invariance, this is not determinant for the universality class. The further myth is related with an interesting aspect of the high probability distribution function that is a solution of a functional Fokker-Planck equation written here. This kappa KPZ is in fact is related with the functional we have shown before. And of course, to solve this functional, or even in the discrete case, to show, to solve the high-dimensional Fokker-Planck equation is very complicated. One possibility is to exploit the short-time propagator that in the apathyntical representation looks like this. This phi function is connected with the potential and will be clear in a moment. And the important aspect here is that it was classically assumed that this distribution, that is the equilibrium distribution of the Edward-Wilkinson problem, is also a stationary solution for the KPZ case. But if we consider this distribution and propagate it with the short-time propagator, we will find that there is a difference, a very small difference. But as soon as we repeat the steps, the propagation steps, we will find that the system departs from the Edward-Wilkinson one. That means that this is not a stationary solution of the KPZ case. And finally, if you want, the fourth myth. The KPZ equation was always considered to fulfill Markov behavior. And if you look at the equation, it's clear that there is no hint about a possible non-Markov behavior. But in the last 15, little more years, there arise a lot of work by mathematicians and physicists, such as Irwin, Heider, Spohn, Ridusal, etc., that exploiting some transformation and analogies with random walks, make a connection with the stochastic matrices, and show that the probability distribution at long times, the statistical probability for H, adopts a general form that looks like a Tracy-Widom-like one, and shows remarkable dependence on initial conditions. If you put a flat initial condition, you obtain trace William. If you put a bubble initial condition, you get a Bames distribution, I think, I don't remember. But the important point is that there are memory effects. From the variational point of view, that is our net, it is possible to exploit the focal Planck equation to obtain a new form of the NEP. And this was done in this paper. And what we get is a gradient expression in which we have a very complicated potential with this functional integral, let's say, that's not clear, but that can be transformed into this one. Look at this fulfills this condition in both cases, but if you make a projection like before, you find that it is unbounded from above and below. If we look at the details of this representation, the functional, we see that we have this term. This term implies an integral from t0, the initial time, to the final time. So we need the whole information of the dependence of h with time along this period. So let me go back. As this is a gradient form, this potential drives the system. Hence, if we have that the potential depends on the trajectory, that implies that the next step, let's say, will depend on how was the evolution before that. So we have here something that looks like the origin, the non-Markovian behavior, in the sense that we can understood that as it depends, as this potential panorama depends on the whole trajectory, we can explain in this way the non-Markov behavior. About results. This, we have been analyzing this work, the behavior, the behavior of the non-equilibrium potential. What we have here is this example of 1, 2, and 3 dimensions. We see similar behavior. If lambda is almost 0, we have this kind of plateau. This corresponds to the Edward-Wilkinson behavior. But as soon as lambda start to become different from 0, we have a maximum and a slope that is linear. And this is the same in the 3 dimensions. Looking at the top, the maximum of these curves, how it evolves in time, we think that we can obtain information about the crossover time from the Edward-Wilkinson regime, linear regime, to the KPZ or nonlinear regime. This is tested here. Is the slope in terms of different values of lambda. We see for 1, 2, and 3 dimensions that it depends on lambda squared, that the slope is 2. And also that the maximum of the curves are a function of lambda. And it looks that in all dimensions is something like the order of lambda to the -1. In one case is 1.414, and another is 0.98, and in 3 dimensions is 0.79, but it's a long one. Respect to memory, if you consider initial conditions like this one, we have that the parameter A determines how flat is the initial condition. If it's very large, we will have the flat condition, but if A is small, we have a kind of wall. And these two curves, these two graphics represents what happens for different values of A, for a constant lambda in 1 and in 2 dimensions. We see that the time behavior changes. And this is an evidence that there is non-Markov behavior, that a strong dependence on the initial condition. We have also analyzed stochastic thermodynamics, in this KPZ case. One of the first papers was this one, Barat and collaborators, in which they analyzed, I think it was a solid and solid model that is in the family, within the family KPZ universality class. And in this work, we have numerically analyzed the existence, the fulfillment of rotation theorems, and etc. And this other paper, Nigeman and Seifert, using some field theoretical techniques, show a thermodynamic uncertainty relation related with the entropy production. We have also produced analytical results of this entropy production. And this work, we do a numerical study separating the system in internal and external degrees of freedom. The external are the collective ones, or the collective one, because there is only one, and showed that some fluctuation theorems are fulfilled. Regarding the analytical results, we can write in an integral idea with integral in mind that the probability for a trajectory that goes from TA at each A at TA to each B at TV in the forward direction, that means TV larger than TA, is with some normalization is proportional to the exponential of the action. The action is defined, the forward action is defined as the time integral of the Lagrangian, the forward Lagrangian, and we can do the same for the backward process. So the probability for the backward starting in TA in TV and going to TA will have also a backward action and a backward Lagrange with a plus here. So from the relation between the ratio between this forward trajectory and the backward trajectory, taking logarithm, we can obtain the entropy production along this trajectory. This ratio is given here, is proportional to the difference of these actions in forward or backward directions, and this term is proportional to the difference of the potential. So the entropy production depends, is directly connected with the potential difference. We have also operating on different relations, find the probability on the probability of some amount of entropy production, and we arrive at this relation that is Crookes-like relation that shows that the probability of a positive production of entropy is exponentially larger than the production of a negative one. We have also obtained some integral fluctuation theorem, as well as another two-R relation. Regarding critical exponents, we can separate the system into the collective and internal variables. The collective variables is this one that is nothing more than the average, the spatial average of H, the height, the surface. We have this constraint that the integral of the internal variables on the whole volume of the system is 0, so implies that the set of internal variables is over determined, and it requires some care, let's say, when doing calculations, both in the continuous or in the discrete length. If we now introduce the family Witch scaling, that is this one here that indicates that a long time we have a finite contribution that is associated with a finite velocity, given final velocity, and fluctuations that came here. Okay, here, beta and zeta are the critical exponent that I have defined and indicated at the beginning. So we can introduce also this relation between the gradient and the time derivative of the quantities, and separate the non-equilibrium potential in 3 contributions. The first 2 associated with the internal variables, and the third one that is associated with internal variables, and with the also enters the collective variable. If we consider one of these contributions, for instance, the second one, what we have is that introducing in this expression the family Bichek scaling, we can reduce all the things, extract the time dependence, and left the rest as a constant. So representing the log, the modulus, the absolute value, because it can be negative, versus the log of t, we have a linear dependence. We should find a linear dependence in some regime from which we can extract the exponent that is this one. So we can obtain another relation between beta and zeta, and we can operate in the same way with the other contributions and find also relation between beta and zeta, and with the other relations that exist between the exponents. We can obtain numerically the exponents in any dimension in principle. This is work in progress. The work that the first results are very encouraging, so we expect to have something very soon. Another possibility is to analyze the time derivative of the potential and do the same, introduce the Edward Wilkinson, the family Bichek scaling, and proceed in a similar way. Finally, another form of treaty system can be through the study of the action in a path integral representation. This is more or less schematically presented here. We have that the exponential enters here, that the action enters in this exponent, and what we obtain is that looking at the time evolution of the action, you obtain this. The black line corresponds to the Edward Wilkinson action. The red one is the KPZ action, and the blue line is the difference between both. This, for instance, can give us some information about the crossover time from the linear to the nonlinear behavior. We can decide that this point or some point around here, or a point around here, then which the different contribution crosses. And in all cases, the representation is similar to this one. This is a line with a slope -1. This is what we have obtained. This is similar, at least is not far from what we had found in other cases. However, if we continue the evolution of the action, we enter into the saturation region. That means that the system reaches the border and the practice. So the KPZ regime disappears. But analyzing this region is possible, again, possible to extract information about the exponents. This is also work in progress. As final comments, let's say that what I have shown is valid for any dimension. It's possible to make it stochastic thermodynamic description and studies for the KPZ system, obtain fluctuation theorems, and even the other forms of the thermodynamic uncertainty relation, make numerical tests of these fluctuation theorems, and there is the possibility of obtaining the critical exponents of new approaches, work in progress, as I said. One of these method approaches is based on a integral representation to the analysis of the action of integral representation. It's possible to obtain at least some approximate form of the KPZ height probability distribution form as we progress, and test some limits to study the different function for the probability distribution function. We can extend the results so far found to thermodynamic, stochastic thermodynamic, to other dimensions without problem, and also the present results or present form of attack problem can be used in other related problems. Well, I thank you for your attention, and because I will now have the chance to stay in the wine reception, I wish you cheers and hug.
Thank you very much for the nice cheers and the nice talk. Do we have time for questions? Somebody showing up, because it's difficult for me to ask a question. I know too little about the equation. There's one person here who knows a lot, but he doesn't raise his arm. Or will you? Thank you.
I guess could you please clarify, you said that if you take the one-dimensional Gaussian distribution and you propagate it, it will not be preserved, the fluctuation dissipation condition. How does that agree with if we look at the continuum, that the probability distribution does not change the Fokker-Planck equation?
Well, let me go back. I don't know how to. Here. Here. Well, what is interesting here is that if you put the Edwards-Wilkinson probability distribution within the Fokker-Planck equation, you will get, and you put 0 here, you will get a solution. It's a stationary solution. But I consider that this is a non-equilibrium one. Why? Because if we propagate, if you look at the different contributions in the short-time propagator, this is the dominant one. This is the following order, and this is a very small contribution. But if you propagate one step, this term will introduce a very, very, very small contribution. As soon as you repeat 2, 3 times, 100 times of propagation, this term that is small start to grow. And you will find that the initial distribution, that is this Edwards-Wilkinson one, starts to depart, and you find that there is some kurtosis, some skewness. But just because the contributions of this small term, I hope I answer your question in this way.
Okay, thank you very much.
I see no other question now, but I hear people outside drinking our wine. So, Horacio, we thank you very much again and wish you a nice evening. Ciao.
Thank you.